Hello. We're going to go ahead and cover Newton's third law today, chapter 5. We'll be wrapping up chapter 6 next week in time for Thanksgiving break. And then after break, we'll be working on some labs and then a project. So I am looking forward to that. Forces and interactions. So an interaction is between two objects. It requires two forces. In Newton's first law and second law, we're only talking about one object and all the forces acting on that object. So determining if an object has net force or not. In a Newton's third law interaction, there are two entities and two forces. So the man pushes on the wall pushes on the man. So two objects, the man and the wall, two forces, the man pushing the wall, and then the opposite force, the wall pushing the man. Equal and opposite forces. So all forces have a pair force, but they act on two different objects. All right, Newton's third law by typical description. Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. And we often refer to this as action reaction. In this image, we have the hammer striking the spike and the spike pushing the hammer. Now, because these forces are equal and opposite, a common misunderstanding is to think that these two forces cancel each other out. If that was the case, then nothing would ever move. Because if every push was responded with a push that canceled it out, you would never go anywhere. That you could never hammer in a spike or whatever. So the reason why the spike goes into the ground is because the spike has a sum of forces. So it has a net force acting on it. And that's what determines whether or not it moves. The hammer also has a sum of net forces, and that's what determines whether or not it moves. Now, of course, the force the spike is placing on the hammer is calculated into the hammer's force equation, but not the force that it applies to the spike. That is included only for the spike. And so when you work out the numbers, you come up with that as long as they both have a net force, then you do have a motion. Okay. A soccer ball kicks a ball with 1,500 newtons of force. The ball exerts a reaction force against the player's foot of what? So a common misunderstanding is to think that it would be less or more or something of that effect, to that effect. So I'm going to have a red soccer ball here, which is really hard to draw a circle with this. Okay. And so the ball is kicked with 1,500 newtons of force. That means that the ball will place an equal and opposite force on the foot of 1,500 newtons of force. So the ball, however, has a net force in the opposite direction, and as a result will move. So you have, it's always equal and opposite. So somewhat less than 1,500 seems tempting, but that is incorrect. Somewhat more, also tempting. It's exactly 1,500. So if you apply 1,500, the opposite force is exactly 1,500. All right, we use the term action reaction forces because, like, you could say the hammer striking the spike is the action, and then the reaction is the spike hitting the hammer. But a lot of times it doesn't make sense to call one the action and one the reaction. So it's relatively arbitrary, which means that it doesn't really matter which force you're calling action and which one you're calling reaction. Often it doesn't even make sense to label them anyway. So it's just one, and then you're just referring to it, the opposite force, as reaction. They occur together, so they're co-pairs. This means that it's a single interaction. Finger touches wall, wall touches finger. So imagine this is a wall, this is my finger pushing on the wall. So the two objects are wall and finger. The two forces are finger pushing wall and wall pushing finger. In that situation, you can kind of figure that the finger is the action force and the wall is the reaction force. But a lot of times it doesn't make sense for one to be an action or reaction. So don't get caught up on that. Neither force exists without the other. So the wall can't push the finger without the finger pushing the wall, basically. They are equal amounts. If it's 50, the other's 50. If it's left, the other's right. So they're always equal strength, but opposite direction. And they always act on different objects. So the action force acts on object 1, let's say, and the reaction force acts on object 2. There are other ways to state Newton's third law. Another restatement or re-expression: to every action, there is always an opposed equal reaction. That is sometimes used not referring to physics, but that's the source of it, is every force has an equal and opposite reaction. Another example of action reaction: the tires of the car push back against the road while the road pushes the tires forward. So the tires push back on the road and the road pushes forward on the car. So anytime you're doing a action reaction, remember that opposite direction thing. So tire pushes on road, road pushes on tire, but if it specifies tire pushes back on road, then you would say road pushes forward on tire. If you don't switch the direction, then it's incorrect. If you leave the direction out in this type of situation, it's actually fine. But if you have a direction, you have to make sure you flipped it. So if it's forward, backward, left, right. Okay, another example. Rocket pushes on gas. Flip the nouns. Gas pushes on rocket. Now, sometimes that won't make sense. So like if your person's picking a flower, hand pulls flower, flower pulls hand, sounds crazy because you don't really envision that the flower is pulling your hand. But that is how you would identify it. So if you take your two nouns and you flip them, that's going to be the easiest way to identify the opposite force. All right, when you step off of a curb, earth pulls you downward. The reaction of this force to this force is. So the rule is you have your two objects. So the two objects in this case are you and the earth is pulling you downward. So we switch the noun, you pull the earth, and then since the direction is specified as downward, we have to switch that to upward. So the opposite of earth pulls you downward would be you pull earth upward. And that makes the answer C. Another practice question. So the opposite being you pull the earth upward, why don't you sense the earth moving? The issue has to do with the fact that the earth is so massive. And so if the force you apply on the earth is equal to the force the earth applies on you, because the mass of the earth is so much larger, the acceleration is so much smaller. And so to show you that in an equation form, so we know that the force of you on earth and on the earth on you is equal. And we could also jump to say that this would be your weight. Whatever your weight is, that would be the force Earth's pulling down on you and the same amount that you're pulling up on the earth. But if we were to take, so this is Earth and this is you, okay? So the forces are the same. Now, force is equal to mass times acceleration. So I'm going to do mass times acceleration. And then over here, I'm going to do the same thing. I'm going to do mass times acceleration. Now, the mass of you is very tiny compared to the mass of Earth, which is very large. Okay. And so as a result, if we have mass times acceleration equals force and mass times acceleration equals force, then for m times a to equal f, a for the Earth has to be very, very tiny and not the same as you. So your acceleration is going to be large because your mass is so tiny. So we still have to have the numbers add up to equal the same thing. So very large mass Earth means very small acceleration, and very small mass U comparatively means very large acceleration. So as a result, you only see yourself moving. So C would be the most correct answer because theoretically that is what's happening. All right, same thing, but on a smaller scale, a cannonball and a cannon. So you have a cannon that's very large and heavy, and then you have a cannonball, which is light in comparison. So the cannonball exerts a force, and the cannon exerts a force on the cannonball, and the cannonball on the cannon. And so the size of F is the same, but the mass of the cannon is much larger than the mass of the cannonball. So, and so these letters are to scale. They're showing you that the mass of the cannonball is a larger number than the mass. I'm sorry, the mass of the cannon is larger than the mass of the cannonball. As a result, if I divide the same force by those two different masses, I end up with a smaller acceleration for the heavier object and a larger acceleration for the smaller object. You can experience this if you've ever shot any kind of projectile. So if you've done bow and arrow, paintball gun, Nerf gun, regular gun, any kind of projectile, there's something called kickback. And that kickback is essentially the acceleration of the firing device that is being forced backward by the projectile. So if you have a very heavy weapon and a very light ammo, there's a very small amount of kickback because you have a very large mass and a very small mass. But the more equally sized there are, the more kickback you're going to feel. So that's essentially what's happening here with the cannon and the cannonball is the cannon will actually recoil. It'll come back towards you as the cannonball fires. Not as much as the cannonball, right? So if you shoot any kind of projectile, even a paintball, the paintball goes really fast. The gun comes back at you, but not as fast as the cannonball. No, I'm sorry, the paintball. And that is due to the difference in the two masses, but the force is the same on each. All right, in this drawing, I am further explaining the cannon and cannonball and actually with better typing. So assume a force of 20 newtons. The cannonball is number 2. The cannon is number 1. Equal and opposite forces. Let's say it's 20 newtons. F1 equals F2. So the force of the cannon equals the force on the cannonball. So those two are equal, which means that the mass times acceleration of each have to be equal to each other. But we know that the mass of the cannon is much larger than the mass of the cannonball. As a result, their accelerations are not the same either. And if we showed a mathematical example, so imagine 20 newtons force, the cannon is, let's say, 20 kilograms times 1 meter per second squared for acceleration. And in contrast, the cannonball is only 1 kilogram, with resulting in an acceleration of 20 meters per second squared. So the cannon has a backward acceleration of 1 meter per second squared, and the cannonball 20 meters per second squared. So a big difference, but there is a backward force. There is some acceleration of the cannon. Question 5 is asking you here, when the cannon is fired, the accelerations of the cannon and cannonball are different. Because why? So that was just explained. I just explained that in the previous section where I was talking about the comparable forces. So if you're not sure, go ahead and rewind and go back and listen to that again. Next question, consider a high-speed bus colliding head-on with a flying bug. The force of impact splatters the unfortunate bug on the windshield. Which is greater, the force on the bug or the force on the bus? Don't be tricked. It's a Newton's third law question. We're talking about equal opposite forces here. Next question. Two people of equal mass on the slippery ice push off each other while they both move the same speed in opposite directions. So if imagine two people even just sitting on skateboards facing each other and then putting their palms together and pushing off. If their mass is the same, based on the discussion we had a little bit ago about how the two forces have to be equal. And then as a result, their mass times acceleration have to be equal. So if the m's are the same and m times a has to equal m times a, then that would make the accelerations also have to be the same. I'm going to talk briefly about the rest of the slides here. This is really, it's about identifying how do you identify your action reaction forces and whether or not a force is actually making something move. So it's all about defining the system, and just about everything in physics, in science in general. What is the system we're talking about? What are the things contained in one unit of something? And in this case would be an orange on a cart being pulled by something. And so that would be our system. Now, if this is our system, the orange and the cart, then the apple is applying a net force on the orange. So we can see that the orange is accelerated. If we include them both in the system, then the internal forces don't cause motion, because we're talking about canceling out here. It would be like if you pushed on your own hand. Like, no matter how hard I push on my own hand, it's not going to make me move. So if I'm defining this system as the orange and the apple, then these forces don't do anything. I would have to include the friction on the floor. So the apple pushing on the floor and the floor pushing on the apple would be my external force, my net external force causing motion of the system. So it's just an exercise in just identifying which thing we're talking about and what causes it to move, which forces are actually doing something. All right, question number 8. The apple-orange system will move with constant speed if. So any system will move at a constant speed if the net forces equal 0. So let's see if there's any that say that. C, a force equal and opposite to the friction force occurs. There you go. Consider the flight of a helicopter. When lift is greater than the helicopter's weight, the helicopter what? So when the upward force is greater than the downward force, what happens to the helicopter? A bird flies by. Equal opposite forces, action reaction forces. Which one sounds like that? Slightly tilted wings of airplanes deflect oncoming air downward to produce lift, upward to produce lift, both A and B, neither A or B. So it's either upward or downward. If the plane wants to go up, it needs to push air which way? Compared with a lightweight glider, a heavier glider would have to push air downward with greater force, downward with the same force, downward with less force, or none of the above. So compared to a lightweight, so the heavier glider would have to do more force, less force, or the same force to stay up. All right, and then at the bottom here, we have a summary of Newton's laws. You will receive a handout for notes for this section next week. And that is it for today.